So welcome. In the last two parts, we have seen different types of pumps and compressors, how they work. And in the last lecture, we have seen how centrifugal pumps work in great amount of detail. We'll talk just now little bit about how centrifugal compressors work or in general how compressors work and what special considerations we need to have for compressors which are not there for uh, pumps. So let's get started. What we would like to talk about first is this is where we are in the course. So although we are saying this part of the course requires 8 hours, and our recorded lecture is only about 1.5 hours or 1.75 of an hour, uh, but extra time is required for you to understand the material. Extra time is required for you to solve the problems which I will tell you at the end of this lecture, and therefore 8 lectures are going to be therefore 8 hours are going to be required to study this module, right? So don't say that lectures is only 2 hours, therefore you will study only 2 hours. Extra 6 hours are required for you to solve the problems so that you are able to grasp this material properly. Just to revise what we had done in the last class so that we are better prepared for this class. How do we define head number, flow number and power number? Why do we need to define? That is another question. What is the importance? What is the advantage? What is the utility of defining this head number, flow number and power number? What is meant by best efficiency point? What is meant by specific speed and what is its importance? And I want you to think about and describe at least two situations where NPSH considerations become important. One of the situations we talked about was bore well, when we had to pump water from a very low level to the surface. We could not have pump at the surface, and therefore we need to locate the pump at a lower and lower level. So the NPSH considerations become important. I want you to think about one more situation. Okay, when we talk about compression of gas, what we mean is that there is a flow coming in. So let's say we are supplying air to the terephthalic acid plant, paraxylene oxidation reactor. So air comes in at a certain amount, certain flow rate, so many meter cube per hour, say 1000 meter cube per hour, 5000 meter cube per hour, and 10,000 meter cube per hour. It comes in at some inlet pressure, some inlet temperature. It is compressed. Now this is the symbol that we are going to use for compressors. It is going to compress to a certain pressure P2, correspondingly a different temperature T2, and the volumetric flow rate. Now here V is not velocity, but here now V is volumetric flow rate. It is coming in and going out continuously, steady state. This is not velocity, although we are using the symbol V. It is actually volumetric flow rate. Volumetric flow rate. Let me just write that very quickly. Volumetric. Excuse the handwriting. Volumetric flow rate. It is actually the Q, but we are going to use symbol V, not for velocity. It is volumetric flow rate. So many meter cube per hour. Q. Okay, we could have said Q1 and Q2 also if you want. Difference between a pump pumping liquid and compressor compressing a gas is that there is a significant temperature and volume change due to volumetric flow rate change due to pressure. Whereas in a pump, although pressure changes, the density hardly changes. So volumetric flow rates don't change. If I have 25 meter cube per hour flow rate at the entry, I will have 25 meter cube per hour flow rate at the exit, because 1 atmosphere and say 5 atmosphere, density is not changing much. Liquid is incompressible. Whereas if a gas, if I have a flow rate changing from, if I have a pressure changing from 1 atmosphere to 5 atmosphere, there will be a significant change in volume, and as a result of that, the internal energy changes and therefore the temperature changes, and we need to account for that with respect to pressure. You have seen in your undergraduate, in your 11-12 standard, you might have studied adiabatic process. PV raised to gamma is equal to constant, and gamma is a heat capacity ratio, Cp by Cv. So typical values of gamma, 1.4 for air, 1.33 for steam. Refrigerants. So refrigerants are very commonly compressed. In your house, there is a compressor. You're using a refrigerator. That refrigerator compresses the refrigerant, makes it into a liquid. It goes to a inside of the refrigerator where it picks up heat, cools down your food materials, and then it gets vaporized. It gets into vapor state. Again, it is compressed to a higher temperature, higher pressure. It condenses by giving out heat to atmosphere. So compressors are very commonly are used all the time for compression of refrigerants. This is one kind of refrigerant called as R134A, and that has a gamma value of 1.2. Methane, natural gas. So you are getting, let's say, gas in your pipeline, natural gas pipeline, Mahanagar gas pipeline. That pipeline has compressed natural gas. Natural gas is typically 90%, 95% methane. So that has a gamma value of 1.32. So different materials have a different gamma value. The increase in pressure P2 by P1 is called as compression ratio. Okay. And if you use this equation, PV raised to gamma is equal to constant, and ideal gas equation, you can get these relationships. V2 by V1 is P2 by P1, and then T2 by T1 would be P2 by P1 raised to gamma minus 1 divided by gamma. So your homework is to derive these relationships. The first relationship is straightforward. It is just coming from this PV raised to gamma. Second relationship requires you to use ideal gas law along with this relationship. Okay, so if a compression ratio is 10, let's say P2 by P1 is 10, which means, let's say, I have an atmospheric pressure as P1, reactor pressure where I'm supplying air, let's say, is 10 atmosphere, and let's say we have an air compressor, so gamma is 1.4. So if T1 is 300, you will find that T2, if you go based on this expression, find out the answer for yourself, but T2 will be 579 Kelvin or 306 degrees centigrade. Now this is a very large change. Now the compressor that we have made, or compressor that is functioning, this temperature is 306. So the material of construction of the compressor, the gaskets and so on, if it's a reciprocating compressor, there is a gasket that runs between the rotating piston or moving piston and the cylinder. So this gasket, these internal materials of construction, they have to withstand this high temperature. So your cost of compressor goes up. Secondly, if volumetric flow rate is 10,000 meter cube per hour at the entry, this 10,000 meter cube per hour, then this volumetric flow rate at the exit would be 1930 meter cube per hour. That's how significant the volume changes and temperature changes are. Okay. So if outlet temperature is high, this compression is not done in one compressor, one stage of a compressor. Right. What we do is we limit this compression ratio. We compress from, let's say, 1 atmosphere to something more, and then and then we cool. So this temperature will be hotter than T1. So if T1 is 300 Kelvin, this will be higher, maybe 400 Kelvin, 450 Kelvin, and so on and so forth. But then we cool back down to atmospheric temperature, and then we again compress, so that we don't allow the gas to rise to this temperature, because sometimes if it's a hydrocarbon, then allowing that gas to rise to higher temperature also is dangerous. Sometimes these hydrocarbons, let's say ethane, methane, those kinds of things, propane, they can reach their auto ignition temperature and they can spontaneously ignite. So you don't want high temperature to be, you don't want the gas to be exposed to high temperature. That's why you compress partly, have a cooler, cool it down to atmospheric temperature without changing pressure, and then you compress again, so that you limit the temperature that the gas is exposed to. So instead of doing this compression by compression ratio of 10 in one compressor, you break it into 2 stages of a compressor, or you do it in 2 small compressors. with the interstage cooling. So this is called as one stage of compression. This is called as the second stage of compression. And typically in each stage we want equal amounts of compression ratio, equal compression ratio. So in each stage we will want square root of 10 because it is 10 raised to half, two stages. So in each stage we will have a compression ratio of 3.16. So if a compression ratio is 3.16 here, and if inlet temperature is 300 Kelvin, this outlet temperature would be 144 degrees centigrade. So you see, substantially less than 306 degrees centigrade. Substantially less than 306 degrees centigrade. Now from one, so this is 144. We allow this to cool from 144 to, let's say, something ambient, let's say 40 degrees centigrade, and then we again compress. So this temperature also is around 150 160 degrees centigrade. We don't reach this high temperature of 306 degrees centigrade. By the way, just make sure that you get this, you do your calculations for yourself and verify that this is right. Okay, don't just trust whatever value you see on the in the lecture. So this interstage cooling, now what it is doing, I remember we are having isobaric process with a change of temperature, cooling. So if it is air that is being supplied, this air would be humid, moist. It would have a percent RH of maybe 60%, 70%. As I compress and as I cool, it will become super saturated. Water will start condensing out. So I need to separate out water from this interstage cooler before I allow air to enter the next stage. I don't want water droplets to enter. If I allow water droplets to enter, these water droplets will carry a lot of momentum because there are very high moving, high velocity parts, and if water droplets hit at a high velocity, it's like a bullet hitting the compressor. So you don't want water droplets to go into compressors. You have to separate out the water, and that's how this interstage cooling. That's why the humidity kind of problems that we did in the MEBC course, we talked about how much water gets condensed and so on and so forth. Okay, little bit about power required and compression, power required for compression. So for example, a three-stage reciprocating compressor is used to compress 3600 Nm cube per hour of methane from 1.95 atmosphere absolute to 61.3 atmosphere absolute with an inlet temperature of 27 degrees centigrade. So now it is a three-stage, right? So it is one, second stage, first stage, second stage, third stage. Now this is second stage. I will have one more intercooler because methane could have water present. I will have one more cooler. I will have one more stage, three stage, and we want equal compression in all the three stages. Okay, I want you to find out the total power. Okay, three stage. So this is 1.95 atmosphere absolute. We want this to be 61.3 atmosphere absolute. So this pressure has to be 61.3 atmosphere. Three equal stages means the compression ratio would be 61.3 divided by 1.95, that is 31.44. That is the total compression ratio between here to here. In each stage we want equal, so cube root of 31.33. That means in each stage we would want a compression ratio of 3.156. So outlet temperature from first stage, again we can use this formula and calculate. Outlet temperature from first stage would be 123 degrees centigrade. Now you might have derived this formula, you might have studied this formula in your 11th and 12th standard, but if not, don't worry about it. You will do this in your thermodynamics course, or there is a course on generation and transmission of mechanical power where we talk about compressors and so on. There you will be able to derive this formula. So energy required for compression is gamma divided by gamma minus 1 RT1. This is for a flow process where it is a continuous flow. You might have derived this expression, you might not have got gamma here if you are doing a batch process like your 11th standard, 12th standard. But this gamma comes when you start talking about a continuous process, a flow process, a flow compressor like a centrifugal compressor or a screw compressor. So P2 by P1, that's the compression ratio, gamma minus 1 by gamma minus 1. So energy required for compression in first stage will be 1.32 divided by 0.32 gamma by gamma minus 1, gamma by gamma minus 1, 8314, that's R. Inlet temperature is 300. Compression ratio in one stage is 3.156, so 3.156 raised to gamma minus 1 divided by gamma minus 1. And you will see this will have, the compression ratio is a dimensionless number, gamma is a dimensionless number, so this E will have units of RT1. So if you take R in joules per kilomole Kelvin, T1 in Kelvin, you will have E in terms of joules per kilomoles. So that's the energy required per mole of compression, per kilomole of compression. Now after interstage, after interstage cooling, if I am bringing the temperature again to 300 Kelvin, then after interstage cooler, if we bring down the temperature again back to 300, then in the second stage of compression, again P2 by P1 will be saying, again inlet temperature will be 300, again it will require the same amount of energy per unit mole. Now if I want power, I should multiply this by the molar flow rate. So molar flow rate, how will we get? We have 3600 Nm cube per hour. N means standard condition. So standard condition means 1 mole will occupy 22.4 liters, or 1 kilomole will occupy 22.4 meter cube. So molar flow rate would be 3600 divided by 22.4 kilomoles per hour. If I divide by 3600, it will be 0.0446 kilomoles per second. So power required will be 3.3 into 10 raised to 6 multiplied by this molar flow rate. It will give me 147180 watts or 147 kW. And if efficiency of this one stage is 60%, that means electrical power required would be 147 divided by 0.6. It will be 245 kW. So 245 kW of power would be required for one stage, second stage same, third stage same. Totally it will require 750 kilowatts of power approximately. You see, and if you had just to give you comparison, if you had the same flow rate or same change of pressure and same flow rate of water, let's say same change of pressure, 61.3 minus 1.95, let's say 60 atmosphere is the change of pressure, 60 bar. So 60 into 10 raised to 5 would be the change in pressure that the pump has to do, divided by rho g would tell you the head that the pump had to develop, multiplied by rho gq multiplied by flow rate. So rho g will cancel, flow rate 3600 Nm cube per hour, meter cube per hour of liquid if I want, that is like 3600 meter cube per hour. So it is 1 meter cube per second multiplied by 60 into 10 raised to 5. That much amount of power pump would have required, but 3600 flow rate if you want to talk in terms of mass flow rate, right? So if I want to talk about mass flow rate, let's say 3600 Nm cube per hour means like 3600 kg per hour approximately, if it is like density is 1, if it's like air, that means it is like 3600 kgs per hour. It is like 3.6 meter cube per hour of liquid if it was water. So flow rate would be 3.6 meter cube 3.6 meter cube per hour divided by 3600. It will be so many meter cube per second. This is 0.001 meter cube per second. So if it was a pump, 60 atmosphere or 60 bar change of pressure multiplied by 1 kg per second or 3600 kg per hour flow rate would require only a power of 6000 watts or 6 kW. This multiplied by this 60 into 10 raised to 2, 6000. So 6 kW. So you see, pump requires so much less power. If it was 3600 kgs per hour of water as against say 3600 kg per hour of gas, you see how much huge amount of power is required for the same change of pressure. Because the volumetric flow rates are large, internal energy has to be supplied. Internal energy goes up because I am compressing. That does not happen for liquid. So if it was a pump, for the same mass flow, pump will require so much less power as compared to a compressor. Okay. Last point in this is sometimes we need to generate vacuum. So if you are doing vacuum distillation or vacuum filtration and so on, so we use Bernoulli's principle for that. So what we do is we have a venturi meter. Only thing is this part of the throat you connect it to another equipment, then you generate a high velocity here. As per Bernoulli principle, pressure is reduced here and you can generate suction. This can be sucked up. You can use it as a gas liquid mixing device, or if it is connected to a vessel, you can generate vacuum in that vessel. So typically in plants, the fluid that is used is steam. So steam goes at high pressure, it generates high velocity here, and then because of the high velocity, local pressure is less and you get suction, you get vacuum developed in a process equipment. We use that for distillation columns or vacuum filtration or anywhere you require filtration. We are not going to spend too much time on generation of vacuum ejectors and so on and so forth. That becomes a specialized topic in itself, but just to make you aware of the principle, it is based on Bernoulli equation. So this part you can read in White's book. It is in chapter 11, sections 11.1 to 11.3. 11.4 we are skipping, and 11.5. The problems from book are these. You can do these problems for yourself. So although the lecture goes on only for about a couple of hours, all the three parts of the three lecture one, part 2, part 3, they together they go on for about 2 hours, but 8 hours are provided for this topic because you need to solve these problems, you need to understand these concepts, and only you will be able to understand if you read from White's book and if you solve more problems and solve them on your own, cross check with your friends and discuss with your friends and so on and so forth. Only then these concepts will become clear. That's why 8 hours are provided, 6 hours are provided, so that you can solve extra problems for yourself. So we'll stop here. The fourth part ends here. Next part will be related to flow past objects.